Our first speaker today is Professor Nial Tanvir. Nial attained his bachelor's in mathematics and physics at the University of Durham. He stayed in Durham to do a PhD entitled Resolved Stars and External Galaxies under the supervision of Dick Fong and Tom Shanks. After a short postdoc in Durham, Nial moved to the Institute of Astronomy in Cambridge, where he was a member of the UK Hubble Space Telescope Support Facility. In 1999, Nial was appointed as a lecturer at the University of Hertfordshire, and in 2006 moved to Leicester as Professor of Astronomy. Nial has sat on many scientific advisory committees and was the Vice Chair of the European Southern Observatory Observing Programmes Committee. In 2002, he was the co-recipient of the European Union Descartes Prize for Research, recognising pioneering contributions to the study of gamma-ray burst afterglows. He was awarded a PPAC Senior Fellowship in 2005. Nial is actively involved in public outreach, giving frequent talks to schools, societies and public audiences, and making occasional TV and radio appearances. Nial.
Well, thanks very much. I don't know if I'll justify all of that preamble, but I'll do my best. I'm also not very sure whether the night after the banquet you'd prefer a very sedate and quiet talk that allowed you to snooze quietly at the back. By the looks of the colour scheme I've chosen, it looks pretty sedate, so that shouldn't be dazzling your eyes too much. Hopefully you will be able to still make out the figures and what have you. I guess, let me tell you the plan. The plan is roughly, and this is what we cooked up between myself and Stephen Smart in terms of what we're going to talk about this morning. So I'm going to be mainly focusing on potential electromagnetic emission from compact binary mergers, as I'll explain. That's going to involve us talking about short duration gamma ray bursts, and in particular I will be trying to cover the prospects and interest from the sort of gamma ray and X-ray side of things in terms of electromagnetic emission from these systems. I'll also talk about or introduce the idea of kilonova emission, kilonovae, otherwise known as macronovae, otherwise known as a bunch of other names that people have come up with, as I'll describe. And that naturally leads us on to the prospects for near-infrared follow-up in particular, and so I'll talk a bit about that. What I believe Stephen is going to focus on is particularly the optical and introducing some of the and describing some of the strategies and the difficulties, the challenges that we have in doing searches for electromagnetic counterparts to gravitational wave events, and he will, I believe, review those and talk a bit more about the future and how the field will evolve into the future. Now, I know you've already had 2 weeks of talks and lectures about gravitational waves, so certainly I'm not going to discuss the gravitational wave side of things any more than I have to. I'm also not going to spend a great deal of time kind of justifying to you the reasons why we believe it's important to try to look for electromagnetic counterparts to gravitational wave events. I think I'm sort of guessing to this audience that's kind of self-evident. We're in this discovery era when this brand new eye on the universe from gravitational waves has opened, and the possibility of putting that together with the information we get from gravitational waves with information that you can also get from electromagnetism, in particular redshifts, host galaxies, environments, the nature of the system that is doing the merging, etc., is obviously, I think, going to be a rich source of physical insight and discovery into the future. So that said, I'm assuming that we all agree that it's going to be a good thing, and so I'm going to focus mainly on what is it that we're going to be looking for and why. Okay, so what kind of sources might potentially give rise to gravitational waves? Like I say, I'm sure you've heard plenty about that in the last 2 weeks. What we're looking for, of course, is something with a time-varying mass quadrupole, and there are a number of systems which could give rise to relatively strong signals of that sort, core collapse of massive stars, neutron star reconfigurations, I'll use the word loosely, but where you've got some very dense neutron star that changes its shape, and that in itself might give rise to gravitational waves. But in fact, the systems which I guess we find ourselves continuously being drawn back to, and in fact will be largely what I consider in this talk, are going to be binary systems involving compact objects. I think, forgetting how I've animated this now. Right, okay. Well, let's just consider, whoops, go back one. Let's just consider the potential electromagnetic counterparts, at least to these top couple of guys here. Obviously, a core collapse supernova, since we wouldn't detect it in gravitational waves very far away, it's likely to be a very strong signal, and so in a sense you don't need me to tell you about how we might search for electromagnetic counterparts in that case. Neutron star configuration, that's perhaps more debatable, but you might look in particular for an event like a magnetar giant flare. Magnetars are highly magnetic, rapidly rotating neutron stars. Every now and again they seem to give off giant electromagnetic flares, flashes of gamma rays, which are very bright. Since these things are not so far away within our galaxy when we detect them to be very bright, and they're thought to be due to a large-scale change in the structure of the neutron star, and so that would be an example of a possible signal. But as I say, what I'm going to concentrate on are compact binary mergers, and in fact, because we're in the ground-based LIGO Virgo era, what in particular we're most interested in are compact binaries consisting of either two neutron stars, a neutron star and a stellar mass black hole, or potentially two stellar mass black holes, but of course there the problem is that the electromagnetic side of things is likely to be much weaker, if at all. So basically we're really going to be focusing on the things in that oval there. Okay, well, why might we a priori expect to get electromagnetic signals from neutron stars, from compact objects of this sort, and in particular bright ones? Well, the name of the game here always boils down to, in the end, gravitational potential energy. And so if I have a neutron star here that you can just about see down in this corner, and I ask myself, okay, let me take a standard size P and drop it onto that neutron star from some large distance, how much energy would the P have when it arrived at the neutron star? And the answer is roughly an atomic bomb's worth of energy. We can do this calculation very straightforwardly, just using Newton's gravitation, and you discover, sticking in a plausible number for the mass of the P, and a plausible number for the mass of the neutron star, and a plausible radius for the neutron star, that you end up with something like 10 to the 13 joules if you do this experiment. So it looks as if there is at least a great energy reservoir there, which, if it could be tapped and turned into radiation, is a very large reservoir to draw on. And so that is the name of the game. And of course, if we were to drop not a P but another neutron star onto the first neutron star, then the energy budget is vastly greater, something like 10 to the 47 joules, which, if you're working in CGS units, then which people typically do in this game, then we're talking 10 to the 54 ergs. So a very large energy reservoir if it can be tapped. And that's of course not so obvious. I mean, if something drops into a black hole, then a great deal of it has already gone in, and so it may be hard to get the energy out. Even if you get it out, what form are you getting it out in? If you get it out in neutrinos or purely in kinetic energy, then you may have difficulty turning that into an electromagnetic signal, and so just having the energy reservoir there is not necessarily good enough. However, it turns out nature, it seems, is at least kind in some respects, and one respect in particular we'll devote now the next part of the lecture to, and that is the topic of gamma ray bursts. So I wanted to spend just a little bit of time going back, reminding you, if you've looked into the field of gamma ray bursts before, or teaching you if you haven't, a little bit of the history and what that implies, what we've learned about the physics of gamma ray bursts, and how then that connects back into this issue of electromagnetic counterparts of GW events. So in fact, we've just passed a golden anniversary. I'm sure a month ago you were drinking a toast to this famous anniversary. If you found yourself drinking a toast and weren't quite sure why you were drinking, then this could have been the answer. The 50th anniversary of the first gamma ray burst to be detected. Now, in fact, it wasn't actually understood to be a gamma ray burst. This detection, I believe, my understanding is that it was only realized sometime later, after the discovery was made using later data, and then they went back to some earlier data and discovered that they had this signal there in 1967, July. Famously, of course, the discovery of gamma ray bursts was made not by astronomical satellites but by military satellites, looking for flashes of gamma rays that might be associated with nuclear tests taking place in space. Instead of finding those, what was discovered was this class of cosmic gamma ray sources, and like I say, the very first one back in 1967, and you can see it looks like a pretty typical sort of event. You have some kind of background of gamma rays, then suddenly, very suddenly, a sudden increase in the count rate, which lasts, in this case, it looks like a few seconds to 10 seconds, something like that, with really very rapid fluctuation. Well, that more or less was the story. In fact, for the next 20 odd years, really, statistics built up. We found more and more of these things, but no one ever found a counterpart at any other wavelengths apart from the gamma rays. The rapid time variability seemed like it should be a good clue. We'll come back to that shortly. But other than that, there wasn't any great lead in terms of understanding the origin of this phenomenon. And so progress, in a sense, observationally was slow. Progress theoretically was certainly active, should we say, and there were very, very many theories proposed as to what might produce gamma ray bursts. Mostly, people considered sources within the Milky Way galaxy, and indeed mostly connected to compact objects like neutron stars. So in the 1990s, this was tested, this hypothesis, and the idea was that if they are connected to galactic neutron stars, then if you build up a big sample, and if you go faint enough so that you feel that you're encompassing a good chunk of the galaxy, you should start to make out something like the structure of the galaxy in the distribution of the positions of these gamma ray bursts. And the Compton Gamma Ray Observatory had an experiment on board which was able to obtain approximate positions, not very good positions, but rough positions for a whole lot of gamma ray bursts. And what did it find? It found that the distribution was almost perfectly isotropic. So this was already very strong evidence by the early mid-90s that really the Milky Way model for the origin of gamma ray bursts didn't look on very good ground. It was still controversial at this time. It wasn't until the discovery in 1997, so we've just been past another anniversary, you'll realise, by Beppo Sachs, of the afterglows of gamma ray bursts, that really we finally nailed the origin down. And what happened was that Beppo Sachs was a satellite that was able to detect gamma ray bursts, but then could reorient and observe the field where the burst had gone off with X-ray telescopes, which were able to provide much more exact localizations on the sky, such that we could then go off with ground-based optical telescopes and obtain images like this, which showed, as we found, that there was indeed optical light associated with the gamma ray burst many hours after the burst itself had faded away. So hours later we could still see this fading afterglow in these lower energy forms of light. And of course, once you've got an optical observation, then that opens up the possibility of getting redshifts and host galaxies. Indeed, as we'll see, this particular case, the host galaxy is here, and in fact this is the little dot here you can just about see is the fading afterglow about 9 months later, 6 months later. So there's the host galaxy. The redshift in this case was redshift 0.65, so this proves finally this long-standing debate was finally resolved. It showed that gamma ray bursts are cosmological in origin. And therefore, the conclusion is that they're by far the most luminous objects known at their peak luminosity. Their intrinsic luminosity is much greater than anything else in at least electromagnetic universe. So what do the afterglows provide us with? The afterglows can be very bright, even when the host galaxies are very faint, and the afterglows are therefore very powerful tools. They provide us with redshifts in the first instance. You can see here this is just an example spectrum. This big deep line here is Lyman alpha, so that's the easiest signal to look for if you're trying to find the redshift. But in fact, many of these other lines that you can see here are also lines that we can identify and use to measure the redshift of this afterglow. In addition to the redshift, though, it also tells us the chemical abundances along the line of sight to the GRB, can tell us about the amount of H1 gas in the host galaxy, the amount of dust, the type of dust, etc., etc. So a whole bunch of things. I'm kind of highlighting that to sort of illustrate again this, what electromagnetism, some of the things that electromagnetism can bring to the party, as it were, if we are moving into an era of multi-messenger astrophysics. There are many things that you can learn from these kind of detailed analyses. Let's move on through. Okay, so let's just think a little bit about what we have learned then from a physical point of view. The amount of energy, if you work out, if you integrate up the energy that we observe at the Earth, knowing the distance to the gamma ray burst, you conclude that a typical, or maybe a rather bright gamma ray burst, if it is emitting energy isotropically, must have an energy about 10 to the 54 ergs. Energy release. So that, if you remember from a few slides ago, is in fact very close to the energy that we said would be released, or at least made available, in a neutron star binary merger coalescence. It's also similar, as it happens for not coincidental reasons, to the amount of energy that is available in a core collapse of a massive star. It amounts to about 10 to the 60 photons, so we're talking a very high photon density potentially here, which turns out to be important as well. What about that rapid variability? We said that would be a key thing. That's a key thing because, of course, things that are big can't vary rapidly coherently due to light crossing time. So in terms of observing something that's big, any rapid variability is going to be smeared out over the light crossing time. The fact that we don't see such smearing, that we in fact see structure, significant structure in gamma ray burst light curves down to sort of millisecond timescales, or 10 millisecond sort of timescales, tells us that the object that's producing the energy must be compact, and roughly speaking, you could say is likely to be less than c times that variability timescale. So something like 10 to the minus 2 c meters. So multiply by the speed of light, a few thousands or tens of thousands of kilometers inside. If we've got something then that is compact, and producing this number of photons, in fact that raises a problem. And it raises a problem because those photons, particularly if they're high energy photons, can pair create, will pair create, and the cross section for them doing so is fairly high. And with that kind of density, then you find that you conclude there should be an opacity to these photon-photon collisions, which is very large, something like 10 to the 13, 10 to the 14 or so. So that would suggest that they should pair create, and in fact that and then the pairs should provide an additional opacity, and therefore we would expect to see a thermal spectrum coming out of an event like this, but we don't see that. We see a very non-thermal spectrum with the energy dominated by these gamma ray photons. And the way round that problem was by supposing that instead the light wasn't produced at this compact size, that instead what was produced by the compact explosion was kinetic energy, basically, that is then converted back into radiation at a later stage. If the amount of, if you can produce an explosion with a bulk Lorentz factor gamma, then you can reduce the opacity by a factor gamma to the 5, and so if you plug the numbers in, then you figure out that if gamma is a few hundred in scale, then it reduces this opacity to order unity, and therefore then you can be happy that you see your non-thermal spectrum. So this suggests that whatever is producing the light from the gamma ray burst is moving at ultra-relativistic velocities. A sort of bit of a caveat, but again somewhat important to us, is that all this requires then very low, what we'll call baryon pollution. Although we're talking about an immense amount of energy, we're also talking about an immense Lorentz factor here, and therefore if you work that out in terms of the rest mass, again assuming an isotropic explosion, it suggests that this amount of this bulk motion here can only be given to something like 1,000th of a solar mass in order to get this required energy. In other words, you can't have too many baryons in the way. So your jet, to keep up this kind of Lorentz factor, even with these sorts of energies, needs to be carrying very little mass along with it, very little matter along with it. Okay, well, some of you will have realised that in a sense I've been sort of, with a bit of sleight of hand so far, I've been talking about gamma ray bursts in general, and of course famously gamma ray bursts come in two populations, and the diagram which illustrates that best is this one, which shows the duration of the burst along this axis and the spectral hardness on the y-axis, and the spectral hardness just basically tells us whether it's dominated by higher energy gamma rays or lower energy X-ray photons. And what you can see is that in a plot like that, each one of these dots represents an individual gamma ray burst, and clearly there is a set of events over here which seem to have quite long durations of tens of seconds and be comparatively soft spectrally, and then another class which seem to have short durations, less than a second or two, and be rather harder spectrally. And traditionally we've often taken a dividing line here at 2 seconds and said that anything shorter than that we'll generally call a short duration gamma ray burst, and anything longer than that we'll call a long duration one. Now you should already be slightly perturbed about that, or at least realise that this is a somewhat, there's a certain degree of woolliness in all this, because obviously these distributions overlap with each other, so one is not able to uniquely fix the nature. If you believe that underlying this are two genuinely separate, distinct populations, two different kinds of progenitor, then clearly you're not going to be able to associate them with full confidence with one or the other, unless they're at some, one extreme end of this diagram or the other. So they overlap. One should also say that the actual look of this plot depends on the detectors that have been used to make it. So the duration that you measure and the hardness is something which depends on the exact way that you define them. And also there's a redshift dependence here. This is the whole population of all the events that were seen by the BATSI instrument. Clearly, if one had a different instrument and was probing a different range of redshifts, then again the figure might look rather different. So I'm just cautioning everyone about that. However, what we can say is that this long class here is the one that we have studied by far the most. It's the one for which our understanding has evolved most during the afterglow era. And I'm going to come and describe that in a moment, what we have learned. The short class are these guys here, and those, of course, are going to be the ones that are going to be of most interest to us from the gravitational wave point of view. But I will digress briefly into the long class just to, again, illustrate some of the lessons which I think we can carry over to our thinking about the other, much less well understood class of short GRBs. So the first big clue as to the nature of the progenitor of gamma ray bursts that came once we had these afterglow localizations was the host galaxies, or at least one big clue. You could look at the host galaxies because you had precise localizations, and you could ask what kind of galaxies are there. There's a long history in astronomy of learning about explosive transients and their nature by looking at where they took place. And what we found, and it might not be too obvious to you sitting there, but trust me, is that these long duration gamma ray bursts are nearly always taking place in actively star-forming galaxies, typically rather small, low metallicity, low dust, rather irregular, high specific star formation rate, which is to say a large amount of star formation per unit mass. And so they're typically taking place in such galaxies. And we could compare that, I haven't got the figure, but we could compare that, for example, to the supernova host galaxies, core collapse supernova host galaxies, and there you discover a wider range of hosts. You'll notice, for instance, here there is only one object which looks like a grand design spiral. And you know that a lot of star formation, certainly in the relatively recent times, has taken place in spiral disks, but they're not represented very well at all in these long duration gamma ray burst hosts. So that suggests a tendency towards low metallicity. It also suggests the fact that we always see them in actively star forming host galaxies, and indeed more than that, nearly always close to knots of current star formation, tells us that we seem to be dealing with a progenitor very likely related to massive stars, very likely related to therefore very likely related, very likely massive stars whose lifetime is less than or order 10 million years or so. In fact, another big clue came really out of the blue, and is still not fully understood really. Shortly after the first afterglow was found in 1998, we discovered this famous case of a gamma ray burst. It's still, even today, the lowest redshift gamma ray burst that we've ever found, and it seemed to be associated with a very peculiar supernova here that you can see at the end of the arrow there. So I put a smoking gun up in the top corner because, that looked like a pretty good smoking gun. It told us seemingly that gamma ray bursts, or at least these long gamma ray bursts, were associated with core collapse supernovae of some sort. On the other hand, the reason why this was always a bit, uncertain is that this is a super low luminosity gamma ray burst. Like I say, it was the lowest redshift that we've yet found. It's a very low luminosity gamma ray burst, and people still debate as to whether or not it's a genuine gamma ray burst or something slightly different. I don't want to dwell on that. But interesting that we make this connection, and indeed what we found from many other observations now over many years is that all the other gamma ray bursts that we find, when we can make a search, we also find a supernova of the same sort, and so it does look as if it did turn out to be a pretty good clue. Let me just, actually, I'll make one last point on this. Of course, the reason that people hadn't, you might think, okay, surely people would have thought core collapse supernovae, obvious possibility as the progenitors of gamma ray bursts. The reason why it wasn't such a popular idea was that whole problem of the baryon contamination. A star is a pretty baryon contaminated sort of region of space. If you're trying to blow material out at highly ultra-relativistic velocities from a star and only carry along 10 to the minus 3 of a solar mass of material in doing so, you may have a problem. We'll come back to that. Sure.
What was the redshift?
The redshift was 0.03. Am I getting that? No, 0.003. So it's basically more or less local universe, really. No, 0.008. I apologise. Yeah. Okay, right. So, so what's the standard picture then that we have now of the explosion that produces gamma ray bursts? And it's a picture that looks something like this. Now, the immediate point you'll notice is that it's no longer a spherical explosion. So I talked earlier on, okay, let's assume that the GRB is a spherical thing. You'll notice already that apparently it's not a spherical thing, it's going to be a jet after all. We'll come back in a moment to why we think the arguments that GRBs are likely to be jetted phenomena. But for now, let me just summarize our understanding of what actually produces the radiation in gamma ray bursts. So we have these two sort of kinds of radiation, if you like, two locations of radiation production. The first is within the jet itself. It's thought, and this is again still not fully understood, but it's thought that shocks between shells within the jet are likely to be producing the prompt emission, those early gamma rays, the thing that triggers the gamma ray satellite, and then the later time afterglow emission we think is caused by this jet hitting any ambient medium, and it may be a fairly tenuous ambient medium around the progenitor, and that then produces this longer-lived afterglow. And the spectra that you would predict from these kinds of these kind of shocks are roughly what we see. Again, there's lots of complexity which is not worth going into for the purposes of this talk. So why do we think that GRBs are jetted? Why did we suddenly change this picture? Well, of course, we know that jets arise all over the place in astrophysics. Whenever we have some rapidly rotating accreting system, then we very often find some kind of jet, and so in a sense it's a natural place to look for an explanation of gamma ray bursts, but that of course is not a highly compelling argument. It's easier to see, as I'm sure you'll agree, that jets could solve this baryon contamination problem, that if a jet is ploughing its way out through a star, of course it can push material to the side, it can eventually evacuate, if you like, a tunnel through a collapsing star, and then continue to pump energy from the central engine up this tunnel, continue to accelerate material until it reaches these ultra-relativistic velocities. And so in that sense, it's certainly an easier model to conceive working in that regard compared to an isotropic explosion. It alleviates to some extent the efficiency problem. So you'll have realized that if I told you that 10 to the 54 ergs was something like the the amount of energy we see in radiation, and if that was the entire energy reservoir of the core collapse event, then we've got an awfully efficient way of producing radiation. That is alleviated if we have a jet, because of course the total amount of energy, we don't integrate over a sphere anymore, we only have to integrate over the opening area of the jet. And so whilst that is still not tremendously well tied down either, that's going to alleviate that problem by 2 to 3 orders of magnitude, we think, because the jets, we think, cover something like 100 to 1,000th to 100th of the area of a sphere. And finally, the observational evidence, which is again subject to plenty of caveats, but will show a nice example which looks very convincing, is that in some cases we see what seem to be breaks in the light curve. So these are the declining light curves of the afterglows in multiple different bands, and what you can see, multiple different filters, observing filters. What you can see is that the behavior is very similar, and it shows a power law, a break from one power law. This is log time against log luminosity, basically, one power law into another power law. That, it turns out, is a prediction of emission seen from an ultra-relativistic jetted source. And the prediction goes like this, that at early times when the front of the jet is moving very fast, there's going to be Doppler beaming, so that in practice you only see a small part of the front of this jet due to that beaming when you observe this source. As it slows down, the Doppler beaming angle widens, and therefore you start to see, from the point of view of an observer looking at this source, basically you see off the edge of the front of the jet. It dilutes the light, if you like, and therefore you expect a steeper decline in the luminosity to occur once this Doppler beaming angle reaches roughly the same size as the opening angle of the jet, which itself may also be widening as time goes by. And that, roughly speaking, translates to roughly speaking, then you can translate the break time that you see into an opening angle for the jet, and so that's where these estimates of jet opening angles of a few to maybe tens of degrees come from. Okay, well, so that's long bursts, and I'm using those, really describing them in the detail that I have, because they're sort of our understanding is much the best for those. And so if we're going to look at the short GRBs, we'd like to learn the lessons that we have from the long GRBs. Why do we want to look at the short GRBs? Well, I've already told you that the long GRBs, we think, are produced by some kind of core collapse event, but a core collapse in a distant object is unlikely to be of interest from a gravitational wave point of view. The market is still open, however, for the possibility that short GRBs may be produced not by a core collapse event, but by merging neutron stars or a neutron star and black hole. So that is why we're particularly interested in them, but what's the evidence that they might be so associated? Well, firstly, let me tell you that short GRBs, I already have told you, are much harder to observe, and our progress in understanding them has been much slower, and that's sort of illustrated by these figures here, which show us in order X-rays here in the top left. The X-rays for afterglows for some short GRBs are shown there, and you can see that they're typically a lot fainter, or right at the faint side of the long GRB distribution, which is shown in grey. So they're faint in X-rays, and in fact, what isn't shown in this figure at all is that there are some short GRBs that even when Swift slews with quite a powerful X-ray telescope and is observing within a few tens of seconds, it still doesn't see any X-rays from these events, suggesting that they really are, implying that they really are very faint. Similarly, in the optical, we find the optical afterglows are faint. which could be consistent with a low density ambient medium around these events. And the bottom line is that at the end of all that, we have very few, we have far fewer short GRBs with good localizations. We have far fewer with redshifts, and in the cases where we have redshifts, in fact, those redshifts in nearly all cases come from the host galaxy rather than from the afterglow. So in that sense, they're less secure. And that's sort of illustrated here. This is a few years old now, but this histogram showing the grey is the long GRB redshift distribution, and the red is the short GRB redshift distribution. Typically, because they're fainter, we're detecting them only at low redshifts. They could, of course, exist at higher redshifts and just be hard to detect. What can we say, though? We can look at those host galaxies, and they immediately do give us a big clue. And it kind of stares you in the face, in as much as what we see, unlike the long GRBs and unlike core collapse supernovae, we see that short GRBs do sometimes live in early type elliptical galaxies, galaxies with no ongoing star formation, and indeed galaxies that have not had any star formation probably for many billions of years. We do also see short GRBs actually in spiral galaxies, but they tend to be a wider range of galaxies than we see for the long GRBs, and the locations of the bursts are much less associated with any ongoing star formation than the long GRBs. So this sort of tells us that whatever we're looking at, whatever kind of progenitor, it's got to be something which is not closely related in time to episodes of star formation, and of course neutron star binary mergers would be such a progenitor, because neutron stars themselves may form in supernova explosions and may be closely associated therefore with star formation, but the merger times can be very long, can be certainly hundreds of millions of years or gigayears, and therefore that could explain that lack of association with star formation. And indeed, when one looks at all of the hosts, you can sort of do some statistics. You have to be a bit careful here because we have very biased and poor kind of incomplete samples, but nonetheless it gives us a sort of ballpark idea that something like 15 to 20% seem to be an early type host. Interestingly, something like 15 to 20% also seem to be hostless. What does that mean? Let me spin off slightly at a tangent here just to look at these hostless bursts. Here's an example of a hostless short GRB. You can see here at the bottom, this little spot is the GRB afterglow inside that green circle. A day later it had disappeared, so that confirms that is the GRB afterglow. But there's no kind of galaxy here. These are quite deep images. No kind of galaxy here, so one is left to suppose that the host galaxy really is one of these other ones that you can see in the field that are numbered there. But if that's the case, then why would the burst be happening outside its host galaxy? And there is again a natural explanation for that in the context of a neutron star binary merger, which goes something like this, that in supernova explosions we know that in many cases they're asymmetric, and one can get the neutron star remnant kicked out of the supernova cloud nebula remnant with quite high velocities. If you had a binary, of course, there would be two supernovae involved, quite likely, and therefore the kicks may be even larger in principle, and so you end up with something like that. This is my PowerPoint skills put to their ultimate test. You end up with something like that, and the velocities, if it is several hundred kilometers per second, that is sufficient. If the merger time is billions of years, then that's sufficient to throw the binary system right outside its host galaxy, particularly if it's a small galaxy that doesn't have a very large potential. So again, that's a sort of consistency argument. Okay, well, we'll come back actually in the next lecture to further evidence that short duration gamma ray bursts are associated with compact binary mergers. For the moment, let's just assume, therefore, that they are. And now let's finish off this bit by asking the question, how good counterparts does that make them potentially to gravitational wave detections? So on the first hand, you'd think to yourself, great, okay, short duration gamma ray bursts, we're already detecting them. Any known ones, any known short GRB, if you put it within the LIGO horizon, would look very bright and would be very easily detectable to satellites like SWIFT or Fermi and other satellites. And so it seems as if we're in very good shape. Moreover, gamma ray satellites, of course, are intrinsically very wide field just by the way that they operate. And so there's no need to worry about scanning areas of sky. Quite likely you'd already be looking, and so you just see this coincident event. The temporal coincidence, because you're talking about something of very short duration, would as well be extremely convincing if you saw something that was exactly coincident in time. Then with a gravitational wave event, then of course that also provides a good deal of strength to the evidence. However, there's a problem, and the problem is the rates. So, actually, I'm beginning to wish I'd not shown this figure because it's a bit complicated. I don't want to bother explaining it all. But bottom line is that this is all the redshifts of the short GRBs that we've measured over the last 10 years or so with SWIFT. And it tells us two things. Well, and that red line then is roughly the horizon for LIGO for detecting neutron star binary mergers. And what you can see is that none of them are inside that red line, so that's bad news. And if you work out the rate density at redshift 0 of short GRBs based on the SWIFT sample, it's something of order 1 per cubic gigaparsec per year. Now, there's plenty of uncertainty in this number, and it could change, but it's hard to make it much higher because, well, it's hard to make it much higher unless you postulate that there are a great many very faint short GRBs that somehow we've just been missing altogether. But if they are very faint, then of course that doesn't necessarily help you very much. So the volume that you're covering out to the range of advanced LIGO, even at full spec, the sort of 2019 specification, is only something like 3% of a cubic gigaparsec. So that would suggest you would have to look for about 30 years or so in order to see one this way. So suddenly it doesn't look so good anymore. Just to highlight that point, the very nearest short GRB that we've seen with SWIFT is 080905A, and that had a distance of about 500 megaparsecs, which you'll appreciate is tricky, shall we say, for LIGO. Okay, so that suggests maybe we should be very pessimistic. If with SWIFT, which doesn't even see the whole sky, it only sees about a sixth of the sky or so, then you might only be talking about one event per century, even with a very good duty cycle for the gravitational waves. However, we could be a bit more optimistic, and so let me give you some reasons for optimism. Well, obviously you have some instruments other than SWIFT which see more than, so altogether we're covering more of the sky. The timing coincidence could of course be quite important because it would in principle allow you to look for sub-threshold events either in the gamma rays or in the gravitational waves. If you detect one or the other, then because you know exactly the time that you're interested in, then that allows you to improve the statistics there and look for fainter events, basically. The orientation you'd expect to be roughly pole on in order to see the short duration gamma ray burst if it's a jet produced at the angular momentum axis of the binary system, and that's also rather better for detecting gravitational waves, pushes the horizon a little further. And of course, neutron star black hole systems could give stronger signals potentially in both cases, and so all these are maybe reasons to be a bit more optimistic. but I wouldn't say super optimistic. I mean, the great news about short duration gamma ray bursts, I would say the bottom line is we will surely eventually see one. And so if all of the other ways of looking for counterparts turn out to fail, then eventually this may be the way it's done. Of course, some people might say it already might have been done, and I mention this sort of for completeness, but famously, many of you I'm sure will have looked at this event. The very first gravitational wave event had a possible candidate detection made with the Fermi GBM instrument. This gamma ray detecting instrument sees a lot of the sky, has good sensitivity, but gives very poor localization. What was seen was apparently a fluctuation here within a fraction of a second of the a second or so of the gravitational wave signal. So that seems to be exactly what we're looking for. On the other hand, you can see yourself that the significance in this plot is not super high, so sort of 3 or 4 sigma kind of height. Given that one is talking a sort of a posteriori statistics, you weren't sure really what you were looking for, particularly from a black hole binary merger, then it's a little hard to know how to treat these kind of statistics. Other people have suggested that the statistics could be done in different ways and better, and you'd get a different answer, but again, I don't want to get into all that controversy, but just to say this is, I suppose, what you'd call a tentative association. The GBM team, as far as I'm aware, their view of this now is that very likely this is a real astrophysical detection of something, but equally very likely it will not turn out to be associated with the gravitational wave event. From a spatial point of view, we're not really in very good shape because the uncertainty in the positional location is very large for both the gravitational wave and the gamma ray event, so they could be associated, but it's not clear. Right, I'm going to kick on then, if I may. Okay, right, so we've talked, I guess we've gone up to more or less the kind of prospects for using gamma rays and GRBs as potential electromagnetic counterparts for gravitational wave events. And following one of the conversations that we just had in the break, I should emphasize perhaps a little more than I did that these reasons for optimism that I gave here, having said that there are reasons for pessimism, because if you just look at the basic numbers, SWIFT really shouldn't detect many short GRBs coincident with gravitational wave events. But these various reasons for optimism that I outlined there do really improve those chances by, an order of magnitude or so. So instead of saying once per century, we might be talking once per 5 or 10 years, which, okay, is maybe disappointing if you want an electromagnetic counterpart tomorrow, but, you're still, I'm with you. I thought it had already been replaced. I was pressing the button as if I'm going to do anything. But I think it's still a realistic hope in the lifetime of SWIFT and in the era, thanks, of the current advanced generation of GW detectors that we may get such a coincident event. So it's by no means, an entirely gloomy story. Anyway, let us move on a little bit and let us talk about the prospects for X-rays. This is closely related, but is slightly different for various reasons. Of course, one thing is that you might fail to detect the prompt emission from a GRB just because you weren't looking there with SWIFT at the time, and you could then spin round and look for the X-ray afterglow. That's probably unlikely to happen all that very often because certainly other satellites are more likely to detect the prompt emission in that case. Perhaps more likely and more interesting is the possibility of using SWIFT to detect the X-ray afterglow of an off-axis event. So we've said that being on axis and seeing a short GRB is unlikely to happen, But the fact that we are dealing with jetted events means not only does the energy requirement go down by 2 to 3 orders of magnitude, but it tells you that the rate, the volume density of these events occurring goes up by 2 to 3 orders of magnitude. It suggests, therefore, that the majority of compact binary mergers that are happening, we're not going to be in the line of the jet, but they will still be happening and may trigger the gravitational wave detectors.
Excuse me?
Yes.
How well established is a typical beaming angle?
I would suggest to you, and other people might disagree, not terrifically well established. So that's why I'm saying, you know, factors of 10 to the 2, 10 to the 3. But there's no doubt there are a few instances which seem pretty strange, instances of GRBs. Just to give you an example of why I'm a bit uncertain myself, even having studied these things for many years, there are some GRBs where we follow the afterglow for years and just see a parallel decline without seeing a jet break, or a convincing jet break. And so that suggests a very wide beaming angle, which somehow seems implausible, you know, many tens of degrees. There are also, certainly if you go back and look at some of the cases in the literature where people quote beaming angles and you look at the actual data, and particularly if you do it now with hindsight, knowing how complex GRB light curves, afterglow light curves can be sometimes, which seem to have nothing to do with beaming and jet breaks, they show complexity. It means that you are no longer very confident about those estimates, basically. So I think you can take a lot of that with a pinch of salt, if you like, particularly for the short bursts, which of course is important. Typically, we find rather similar beaming angles for the short bursts when people have made estimates. Again, degrees, perhaps slightly wider, 10 degrees or so, typical, but again, I think lots of uncertainty. However, let's assume they are beamed. Why would there be a prospect of seeing a burst off axis if I've said that you need to be on axis in order to see the gamma ray burst? The reason is that as the front of the jet decelerates, we already said that the Doppler beaming angle widens, and so there comes a point where if you were off up here, you would have never seen the on-axis emission, but you do start to see this off-axis emission. Of course, by this stage it's much fainter, so you know we're not talking about nearly as bright an event, but nonetheless, if we're within the LIGO sort of region, it's relatively nearby, and so that kind of compensates, and so you know it is a viable option. I think in the interest of time, I won't try and explain this diagram fully. I'll just give you the conclusion. The conclusion is that when people have done simulations of the prospects of looking for these off-axis GRB afterglows associated with gravitational wave events, you do indeed find that it's viable. You may find some, but again, it's somewhat pessimistic. You perhaps only are going to, depending on your strategy and indeed depending on the unknown nature of the jet and the ambient medium that it's sitting in, and many other unknowns, you don't expect to see more than a few % of gravitational wave events this way. But nonetheless, that still, you know, is a worthwhile thing to do. At least it is a signal that you do expect to see. I'm going to now highlight, if you're going to do that with SWIFT, of course you've got to start dealing with the practicalities of doing it. The SWIFT X-ray telescope only has a field of view of about 1/5 of a square degree. So if you're wanting to map out tens or hundreds of square degrees associated with a gravitational wave error region in the current era, or in the 2-detector era certainly, then that's obviously very challenging. And so I'm going to highlight some of the practical steps that we take to try and deal with that. This may well overlap with some of the points that Stephen makes later, but I'll just introduce the idea now at this stage, which is, of course, that if we're looking in the relatively nearby universe for these counterparts, then they're likely to be taking place in galaxies which are relatively bright and easy to see, and for which the distances may already be known from the redshift. So if I plot out a map of the galaxies in the local universe out to a certain redshift, then it looks something like this. There are some caveats here. This is a rather incomplete map in the sense that faint galaxies aren't represented. on here. Intrinsically faint galaxies are not there, so it's sort of biased to the brighter galaxies. Of course, that may be where most of your gravitational wave events are occurring, or may not. However, it does allow us, if one is looking in some big region of the sky and wanting to look for counterparts, instead of trying to scan the whole region, you could at least target known galaxy positions, and that way save yourself a lot of time, even if you risk, of course, that you might not target the actual host. How much time do you save? We did a simulation a couple of years ago specifically for to help us with planning SWIFT follow-up, and we discovered basically in these simulations, again I'm not going to describe it in detail, to cut a long story short, you saved yourself something like a factor of 5 or 6 or so in terms of the number of fields you needed to look at to find these simulated events that we put in by hand by doing this galaxy targeting approach. And so it certainly makes your follow-up much more tractable. I mean, to put it into some kind of context, if you've got SWIFT zipping around the sky trying to fill in this whole error box, you want to spend a little time at each position in order to go deep enough to see your counterpart. And that is a problem not just because you run out of time, but it's also a problem because SWIFT does make a lot of maneuvers every day, but of course one worries about trying to get too ambitious and having it slewing very, very rapidly, continuously, potentially is a risk to the spacecraft, and so it's something one has to be a little cautious about. Okay, let me spin through this a little bit just to say that SWIFT did put this into effect in the 01 and indeed has continued in 02, and for the very first event it only looked at a relatively small number of fields illustrated there, but subsequently by improving the flight software we were able to do a run where it observed again the same error region, although much later after the event, but the same error region as the first burst within a day, and managed to cover all of these galaxies there that you can see highlighted in red. So this strategy seems to be working out. Okay, so this was where I was expecting to have the break for part one, so I'll just quickly list the conclusions. There are good indications, I think, that short duration gamma ray bursts are the product of compact binary mergers involving neutron stars, at least one neutron star, but there'll be some more evidence to come. A short GRB within the advanced LIGO horizon is an unmissable signature, and even more distant short GRBs could allow these kind of sub-threshold searches, as I explained. Alternatively, one can look for off-axis X-ray afterglows, and that is indeed a project that SWIFT is actively engaged in. Okay, right, so that's part one. So part two, let's see how quickly can we do this. Okay, what have I got here? I've got all of the chemical elements, I'm sure you recognise that, arrayed there by atomic number, and the logarithm of their relative abundance sort of in the universe up the side there. So, of course, hydrogen and helium are by far the most abundant elements. The other light elements, lithium, beryllium, boron, we understand are largely produced in the Big Bang. And then all of the elements here up to the ion group elements are largely produced in stellar nucleosynthesis, fusion in the cores of stars, and then gets sprayed back out into the universe, particularly in supernova explosions. Question is, and you might wonder where I'm going with this, you might not, maybe some people see the connection, but what about all these other elements here? What you can see is that they're several of orders of magnitude less abundant than the elements up to iron, but nonetheless, they clearly exist. We know in nature all of these heavier elements exist. How are they produced? Obviously, they're not energetically favourable. You don't produce these elements and create energy, and so they're not going to be produced in great numbers. Okay, I'm just spin through that. And so that was a bit of a mystery. That was a mystery, back in the 1940s and 50s when it was realised that, when people were first starting to understand the processes of nuclear synthesis. One should say, of course, that the zigzag appearance of this curve is just due to the favouring of even pairing of nucleons, of protons and neutrons, and those make slightly more stable nuclei, and therefore they're slightly more common. What one should try and do is sort of take this picture and remove that odd even numbering to see how the abundances otherwise vary. And what you'll notice is, obviously, there's some kind of overall decline here, but there are also some peaks here as well. Okay. So people wanted to understand how these heavier elements were made. And they're made, we think, by and large, by neutron capture. So neutrons can, in certain environments, merge with a heavier nucleus like that, and then the neutron is captured. That can emit some energy. In many cases, it's going to create an unstable nucleus, and so that will beta decay. It'll turn the extra neutron that you had in the first place into a proton, and so you'll have made an element which is 1 up in terms of proton number on the periodic table. So these ideas were worked out particularly in an astrophysical context in the 1950s, and Fred Hoyle was one of the leading people in that work. And what that then might lead you to expect is that you would expect to see peaks of these elements that corresponded to the nucleon magic numbers, closed shells in these in the quantum mechanical shells making up these nuclei, and those magic numbers happen at these particular numbers here. Obviously, the early ones are sort of washed out, but the higher numbers there we might expect to correspond to some of those peaks that we saw in that previous plot. Okay. Now, how does this nucleosynthesis proceed then? If we're going to make these heavier nuclei like that, what we're saying is we'll add a neutron, we'll let it beta decay, and we'll chunter our way up the valley of stability that way. So sometimes you'll add a neutron and it'll make another stable nucleus, and then eventually you'll add another neutron and it will become unstable and it will decay. Beta decay is happening diagonally top left in this diagram, and so you'll basically work your way up the black valley of stability there in this diagram of neutron number versus proton number. Okay, so that all seemed to make sense until you looked at the actual distributions, and this figure here was the one published in the famous B squared FH paper in 1957, and so it's a somewhat schematic figure and actually sort of shows the point much more clearly than the real data, so I'll stick with this somewhat schematic version. And what you see is the elements up to iron, and then you seem to have three broad kind of peaks, but they're split in fact between a peak actually at the neutron magic number, and this is atomic weight here listed now, which is labelled S, and then these peaks that are slightly lower atomic weight labelled R. The S numbers we've already said, the S peaks here we can understand as being particularly stable, highly bound nuclei because of the closed shell, closed quantum shells in the nucleus, but the R peaks are harder to understand. And this was explained, and indeed this is where the letter comes from. It became understood that this must be due to very rapid neutron capture, such that the neutrons are being captured at a much higher rate than the typical decay rate, so that one can build up very neutron-rich, highly unstable elements before they finally do decay. And I'll show a movie in a moment that will sort of illustrate this and maybe firm up that understanding and why that then produces these R process peaks. But first of all, the question is, why are we interested in this? Why am I telling you about nucleosynthesis, R process, S process, etc.? Well, the reason is that if I'm going to very rapidly build up elements by neutron capture, then I would like to have an environment with a very high density of neutrons. So you can see maybe where we're going. If we have a very high neutron density environment, where might that be? Traditionally, people have said, well, maybe it happens in core collapse supernovae, but it turns out that it is rather hard to get this to work. And so, less popular, but now increasingly popular, is the idea that maybe this happens in neutron star mergers instead. Okay, get the little movie to go. So, how would that work? So, here is a simulation, one of Stefan Rosbog's simulations of two equal mass merging neutron stars. Actually, I don't think they're equal mass, slightly dissimilar mass, yes. So you'll see that there's a material tidally ejected during this merger. It turns out you also expect material to be ejected due to neutrino winds, and some material that's maybe ejected during the sort of mechanical collision of the two bodies as well. So you have these different ways in which these mergers produce a final remnant, which is probably most of the mass, and it may well be a black hole, but also a certain amount of ejector. And that ejector, of course, naturally is going to be very neutron rich. How does that work in terms of this nucleosynthesis idea? What material might that ejector turn into once it decompresses? It's no longer under the gravitational field, it decompresses and is going to make some kind of regular matter, but what kind of regular matter is it going to be, given that it is a naturally very highly neutron-rich, low electron fraction kind of material that we're working with. And so here is a simulation which I will run, and basically the starting point is at very early times. You expect this highly neutron-rich distribution here, and if we let that run, then we can see how that evolves. And you can see that as neutrons get captured onto those nuclei, time is now starting to run to more sort of sensible numbers. And then when the nucleosynthesis stops, having reached peaks at these magic numbers due to this very rapid neutron capture, the beta decay then pulls you diagonally onto the stability line, but at a position that's now offset from those magic number values. So I'll run it again just to illustrate the point. So you can see how those magic numbers, which are labelled here in these vertical bars, how the isotopes tend to cluster up around there, and then the beta decay pulls you diagonally, making those second offset peaks. So that's broadly, in a hand-waving way, the argument. Obviously, the details are very complex, but what you find, in fact, is that this doesn't depend very much on the actual binary parameters. It's a rather robust prediction that if you start out with these kind of conditions, then you end up with a distribution of our process elements which matches that seen in the solar system and elsewhere. And so that was proposed way back in the 1970s originally as a possible location for our process production. And, one has to appreciate this is a pretty big mystery, the origin of all these heavy elements. And so it's a very interesting thing if indeed it does tie into neutron star mergers. Okay, where is that leading us? From the point of view of electromagnetic counterparts to gravitational wave events, where that's leading us is that if all this radioactive decay is taking place, then it should naturally energize the material that was thrown out during the merger event and make it a bright and explosive event. An event that you could see and therefore has been given a name, a kilonova or sometimes a macronova. So there's quite a long history to this idea as well. This goes back to the 1990s. What has changed just more recently in the last few years is our understanding of exactly what these things should look like. And the reason is that it turns out that the newly synthesized R process elements themselves, particularly the lanthanides and actinides, they have F-shell valence electrons, which leads to a very large number of potential electron transitions which can take place, which is to say potentially millions or even hundreds of millions of electron transitions that you have to account for. That tends to produce a very large number of absorption lines in the optical, and therefore leads to very high opacity in the optical. And the conclusion is that the emission, instead of coming out in the optical, which is where you might have imagined it would come out just based on thermal considerations, is likely to come out in the near infrared instead. And so the spectrum from a particular simulation of this kind of event is shown here. It's evolving with time, but after a few days, the emission is largely here in the near infrared. So if I put the boundary between the near infrared and the optical is about here, and so at early times there would have been some optical light, but by late times that's almost entirely absorbed and it's coming out in the near infrared instead. In terms of what you expect to see for the light curves, the prediction is, if we look in the right-hand panel, that in the near-infrared bands, these are the top ones here, you expect to see an event which rises in brightness over a few days and then has some kind of plateau for a few more days before fading away, whereas the optical light should be, according to these models, much fainter. The reason this hadn't been appreciated earlier was that people had, for simplicity's sake, just taken ion opacities, which are more conventional in the supernova game, and used those, and then you got a much more equal sort of light curves between the infrared and the optical. But using these R process opacities, generically one ends up with much fainter optical and brighter infrared, and also spread out more in time. So the peak in the light curves happening at several days rather than within the first couple of days. Okay, so there's a prediction from theory, and the question is, does this actually happen in nature? So of course, one place we think we have, well, what we'd have liked to have done would have been to find an event like this associated with a gravitational wave detection, but of course those hadn't been made at that stage, and indeed still haven't been made with neutron stars. And so instead we look for the other place that we know that or think that compact binaries emerging, which is to say short duration gamma ray burst. Now these are rare, as I've explained. They're particularly rare at low redshifts, which are low enough in order to look for an event like this. But fortunately, one happened in 2013, in June 2013. Here was the gamma ray light curve, and it shows it was an undoubtedly short GRB, because this is really very short. That's just a tenth of a second there. So it's a very nice short burst. The redshift, well, turns out to be about 0.35. The interesting thing was that we went away and looked at this short GRB with the Hubble Space Telescope and saw some light about 9 days later in the infrared, but not in the optical. So the kind of big thing in the background is the host galaxy. Within the little red circle, I'm not sure how clear that will be from where you're sitting, but within the little red circle there is a little blob, which is the bright infrared source. Some days later, some weeks later rather, it had faded away, and so if we subtract the two images, this is what you see. So sure enough, there was an infrared source at about a week, and no optical source. So you ask yourself, is this such a kilonova, or could it just be the light from the GRB? So in order to assess that, what we did was plotted the fading afterglow light curve, and so let's focus on the one in blue here, which is the optical light curve in blue, and you can see that it starts its power law decline here and carries on, it seems, a fairly straight power law. So if one extrapolates it like that, then it's no surprise that you don't detect anything at 9 days. In the infrared, though, the data are not as good, but if we assume it follows the same power law, which is what you generically expect for afterglow behavior, then you would expect the afterglow, indeed in the infrared, also to be invisible after 9 days. Instead, what we found, the thing in the orange circle here, 1 data point is all we have, but we find a measurable and indeed quite bright excess in the near infrared. So it's this 1 data point which is the one example, I would say, of a convincing detection of something that looks like a kilonova that we've so far made. Why do I say it looks like a kilonova? Well, if one put the light curves that have been predicted by the Barnes and Kaysen models on this figure, they span some kind of range here, but they're these light orange curves, and you can see that they more or less match up with where we find the light in practice. In fact, it turns out that we're a pretty good match with their models, which have an ejector mass of about 5% of a solar mass. So we were quite happy with that. It seemed like confirmation. It turns out, though, subsequent work suggested that that 5% was quite a high number. And it's still debated as to whether or not what that means. Most simulations of these kind of binary mergers are finding ejector masses less than that, less than 1% or so. However, there is a degree of quite a large degree of variation in the models, and that's illustrated, in fact, in these plots here. These are rather more recent light curve predictions, again from Stefan Rosvog, showing in this case 2 neutron stars compared to a neutron star and black hole. And you can see that the neutron star black hole system, much higher mass ratio, more material ejected from the neutron star, produces a considerably brighter event in these predictions. So there's a great deal of uncertainty here in this game, and I think it's still a crying need for further observational input, and I'm going to come on to what further observational input we have in a moment. And indeed, the theory also is still in many ways at a very early stage, even though these are very complex and sophisticated models that go into this. It is a very complex kind of situation we're dealing with. So let's just realize that we're talking about understanding objects like neutron stars where we don't know the equation of state, for instance, and the structure of the neutron star very well. We're merging them with simplified physics. So, one tends to find that you can either do one thing very carefully and another thing not so carefully, or the other way round. So you can do these things in general relativity, but then trying to monitor all of the nuclear physics, the atomic physics, the radiative transfer, the neutrino transfer, is all, each of those is potentially very complex. So it's really very challenging. Just as an illustration of that, and I'll mention this somewhat in passing, if anyone wants to come back to it, there was a recent paper by Fontes et al. Which suggested that line smearing of those many lines in the optical, they only need a little bit of smearing and broadening in order to really wipe out the optical and indeed the near infrared as well, very well. And they suggested, in fact, that one should be seeing this emission peaking much more into the mid-infrared instead, and that would be considerably harder to observe, and of course doesn't match what we seem to have actually seen in one case. Another way, in fact, it has been proposed that the emission might be brighter than you first thought, could be if there is, in addition to the radioactive heating of the ejector, if there is also ongoing heating from the central engine. So whatever the remnant is that's left over, the black hole or maybe magnetar, central engine, a central source, inside this overall ejector, so the ejector's going out there in pink, if that is continuing to be active, maybe continuing to accrete or lose rotational energy, then that could produce, let's say, an X-ray flux on the inside of this the ejector cloud, and could continue to heat the ejector and could make it brighter as well. Particularly interesting thing in this regard is that there does also seem to be an excess in the X-rays. If one looks at the XMM observations of this particular event, they also seem to increase over on this time scale of some days. which could suggest that some of these X-rays from the central engine are coming out, and we're seeing those. And so it potentially is another X-ray signal one might look for associated with such events, a more isotropic one than previously discussed. Okay, I'll spin fairly quickly through a couple of other suggested kilonova signatures. So once we'd found that one fairly convincing case in 2013, people went back to have a look at some historical data sets for short GRBs to see, okay, is there any hint in any of those that there could be kilonova emission? People had already looked, of course, for this kind of signal, but what had changed was this idea that maybe we should be looking in the redder wave bands rather than in the optical. And there were some hints, so in a couple of cases, and so one of them, this was another one of the very early short GRBs to be well localized, and again it's somewhat complicated to explain this figure, but basically the bottom line is that if one looks now not really in the what's normally thought of as the near infrared, but the sort of very red end of the optical, the I band, then there seems to be some kind of excess in terms of these points here compared to the decay that was seen in the bluer bands. So that's the green line there, and it seems that the red points are rising above that, possibly indicative of a kilonova kind of event. But if this is true, then one which is giving a fair amount of its light, even in the I band, at less than 1 micron in wavelength. Another event for which such a signal has been, I would say, cautiously or tentatively claimed is this GRB here, 060614. Anyone who is kind of familiar with the GRB history will know that this actually is already a controversial burst. It's by no means clear that it is a short duration GRB. In fact, it's normally viewed as a long duration GRB, but with some question marks. And so it's not necessarily the most obvious system to be looking at. However, what was seen here again in the I band is again an excess over what you'd see in the bluer bands, but now peaking actually at a couple of weeks after the burst. And so this certainly doesn't fit very comfortably with the existing kilonova models, but nonetheless it's an interesting source, and if nothing else, it is telling us that in events like this, clearly there are things sometimes going on at later times that we don't have a full understanding of, and so all of interest. Okay, I want to spend a few minutes just describing briefly then, if we say that kilonovae emitting in the near infrared seem to be associated with compact binary mergers, then what are the prospects for using them as electromagnetic counterparts of gravitational wave events? And I want to describe a particular project I'm leading that's attempting to do that, and it's not an easy thing to do, as I'll explain. However, I think it is a problem which is at least tractable at some level. And the way we are approaching this is particularly reliant on this telescope here, the Vista telescope, based in Chile. The reason this is the most interesting telescope to use for this game is that firstly it's a 4-meter telescope, so it's pretty big, but in particular it's got the biggest near-infrared camera of any large infrared telescope in the world. So that's sort of illustrated here in this panel. I guess it's not too clear, it seems to be rather faded on the screen here, but the Vista camera is the thing, those 16 red detectors there, and you can see that by comparison the second biggest camera is about a third of the size or so, and then other cameras are smaller. So basically it covers a lot of area on the sky. It's still less than a square degree. Oh, our project is called Van Rouge. I'm sure you all wanted to be reminded of wine at this morning. Don't ask me what it stands for, I can't remember. But what we can do with this telescope, even though its area is less than a square degree, obviously you have to go about tiling to try and build up areas of tens of square degrees to be of interest in these gravitational wave follow-up searches. And so I'll just highlight the two cases from '01 and just show you what we did there. In the first case here, for the 1509-14 event, you'll remember, I'm sure, people will have commented, that this event, the error region, overlapped with the Large Magellanic Cloud. And you can imagine waking up or being woken up by this alert on September the 14th in the morning, or the 15th, whenever it was, on my morning, and you had to decide where you might point your telescope at to do your follow-up, because you couldn't do the whole region. And I kind of looked and I thought, oh, the Large Magellanic Cloud, well, that's kind of fishy. Who knows, maybe something's happened in the Large Magellanic Cloud which has given rise to this gravitational wave signature. Of course, at the time I wasn't party to this this image here, and so that might have convinced me otherwise, but anyway. So we basically spent our time tiling the Large Magellanic Cloud, and it shows that at least it could be done. Over the course of a few nights, we managed to cover the entire region, about 40 or 50 square degrees of the Large Magellanic Cloud. Of course, there are a lot of things in the Large Magellanic Cloud. There are many things which vary. Not so many things which even looked slightly like the signal that you might have been looking for. So in the end, of course, nothing of interest. But it was our first run out and showed at least that we could do this kind of mapping. And there's the Large Magellanic Cloud, and there is just an example of a variable source. So you can just about see maybe there's a star in there that's disappeared there. The second event, or the event in December, the Boxing Day event, 1226, again, of course, the problems you run into when you're doing this sort of game is Vista is in the south. We would have liked to observe areas of the error box in the southern hemisphere, but these areas were very close to the sun and so weren't really observable. So instead we chose to do a section of the northern error box here, which was at least fairly high probability and we could still get to with the Vista telescope. And so that was the scan we did on that occasion. And here you can see some representative data, which actually, again, we didn't find anything tremendously interesting, but we're still sort of working on trying to improve our pipelines for the analysis of that. So just to summarize this VISTA program, we now have a lot of time awarded over 3.5 years, although some of that time has already been used. Some of that 3.5 years has already been used. We plan to coordinate closely with the VST telescope, which is the ESO telescope in Chile, which works in the optical, so it's a sort of similar optical survey telescope. We also have time allocated on a bunch of other telescopes to do follow-up of any sources that we see, because of course the concern is that you may see an object which is varying, but of course it may have nothing to do with the gravitational waves, and so you need to try to follow it up to see if its behavior looks like that you might expect from a kilonova. Also, in order to get maybe the redshifts, for instance, for a host galaxy, if there's a host galaxy present. Prioritize, this is obviously stating the obvious, the triggers which have a high probability of a neutron star in the system, because we really don't expect to see such things from black hole mergers. Again, target local high densities of local galaxies. The strategy is still evolving, and I think will evolve as the gravitational wave detectors become more sensitive. It'll evolve further, but the baseline idea is to start with 3 filters spanning a range of wavelengths in the near infrared over the first week, and then revisit after another couple of weeks in order to get a second epoch to compare to look for the variability. The depth we reach, typically it depends at what sensitivity you're talking about, but around 20.5 to 21, and we would, in O2 at least, we were aiming to cover kind of 50 square degrees at a time per trigger. There is existing VISTA imaging of most of the southern sky, and so that's very helpful. It means there's an earlier epoch we can go back to in order to compare to if we see anything. And then, of course, report any candidates within the wider LIGO Virgo EM counterpart follow-up campaign. Okay, I want to finish with, so, there's nothing yet to report from that VISTA program, but I think it's very hopeful for future years if these kilinovae turn out to be common and if their properties are like the ones we saw in the case of 130603b. Let me just finish off by trying to bring you up to date, because you might well look and ask me, it's been 4 years since you got that first event, why do we not know a whole lot more about these things now? And that boils down to the fact that short GRBs at low redshifts are rare and they're difficult to follow up to these kind of depths. So we need HST typically, and even then is challenging. And so let me bring you up to date with the ones that there have been which were sort of candidates for this kind of follow-up, and I'll just explain what we have learned. So there was one on New Year's Day in 2015, which turned out to be in a galaxy at redshift 0.14, so that sounds very good. It's an unusual galaxy though, as host galaxies of GRBs go. For one thing, it's X-ray bright itself. So that really confused the situation in the early days, because the X-rays that were being detected by SWIFT, it turns out, were largely coming from the host galaxy rather than the afterglow. It was only after some days that it was realised that there was an optical afterglow here in this green circle there. It's also an unusual burst because it's the very shortest that's been detected by SWIFT, and so it was unclear for some time at least whether or not it was a regular short GRB or whether or not it might have, until you saw this offset, it might have something to do with the AGN, for instance. So the limits that we got in that case on any kind of kilonova were not very deep. These are ground-based limits, and again, I'm not going to try and explain this whole figure, which is a bit complicated, but basically the limits here are these green triangles there, placed then in a context of an absolute luminosity scale showing where one could have reached with a VISTA-like survey if this event had been at 200 megaparsecs. All of the grey bands here are various kilonova models, and you can see that we really barely constrain them with the observations of this particular event. A few months later, we had another case which looked very promising at first, but now it turns out we're really not sure if it is promising, and I'll highlight this to show you the problems in the field. So here was the afterglow of the GRB in the green circle, so that looks very nice. Here was the supposed host galaxy. If you see a situation like this, if you can just look at an image like this and you can realize that, there are not many galaxies that are this bright, and so it looks unlikely to be a chance association, but you can't be sure. The redshift of this is 0.3, so it looks promising. We obtained HST observations, which are there, shows that the galaxy with HST is seen to be a nice big spiral galaxy. However, when you look at the actual location of the GRB, again, this probably doesn't come out too well on this screen, but you can see there is something faint there behind the GRB, something extended. Once the GRB had faded away, there's clearly some other kind of galaxy here. So then you're left with the question, is that really the host rather than this? Is it at the same distance as this, or is it further away? We don't have any very good constraints on the distance of that faint galaxy. It seems to be less than the redshift of 1.2, probably more than the redshift of 0.3, but we're really not very sure. So this has turned out to be a very difficult one to analyse. Let me finish off on what will be, I think, shortly, but we're still working on it, perhaps the next sort of exciting one. So this is one from last year. Again, you can see we're playing the same game. We find the afterglow. We suggest that the nearby thing here is the host galaxy. You measure the redshift of the host galaxy, it's 0.16, so that tells you it's relatively nearby. Still not near enough, realistically, probably, to see a gravitational wave event from this object, but realistically, equally, a very good event to be looking for kilonova emission. So we're still working on it. There is the afterglow. However, provisionally, there does appear to be, when we combine our ground-based and space-based data, again some evidence for a colour change here. So going from early times, the blue points are the optical, the orange points there are the infrared, and although it's not crystal clear, it certainly looks as if the optical is following a fairly nice power law decay, whereas the infrared appears to be bumping up again with some kind of excess that we don't see in the optical. So this is still very provisional. One thing we can say is that if there is a kilonova, if we decide that this is a kilonova signal, it's certainly much fainter than the one seen in 130603b. That, of course, wouldn't necessarily be a surprise. It would be consistent with what we said before, which is that the models seem to suggest there should be a wide range of behaviour, in fact, particularly in terms of brightness. And so to find a faint one wouldn't be a surprise. Interestingly as well, we also find an excess of X-rays as well in this particular case. So it seems that there are X-rays, there's an X-ray signal seen by XMM at a few days after the burst, just as there was in 130603b, which seems to be in excess of what you had predicted by extrapolating the earlier X-ray behaviour. Okay, so I'm finished. Just conclusions for the second bit then. Compact binary mergers potentially also perhaps the predominant site of our process element production in the universe. So that's something which probably doesn't interest you tremendously if you're interested in gravitational waves. However, it is of interest, right? Because in order to work out whether or not they are dominant sources of our process production, what we need to know is not only how much nucleosynthesis is likely to be produced in each event, but also how many events are there. So the event rate of compact binary mergers is an essential part of this calculation, and of course that's something that ultimately we'll understand from the gravitational wave detections better than any other way, I think. The high opacity that you predict, and Stephen may explain why there are some situations in which actually you predict the opacity should be lower and therefore you might see more optical light, but just in terms of what I've described to you, the baseline expectation is to see this high opacity and therefore push you to looking in the near infrared rather than in the optical. And that sort of seems to fit in with the observations such as we have. Well, those observations in particular consist of this one burst with this late time infrared excess and some tentative hints in other cases yet still to be decided. And then finally I've described how we're going to try to do this follow-up in the future and hope to find one of these infrared kilonovae with the Vista telescope. Okay, I'll leave it there. Thank you for your attention. And sorry for my chesty voice.
That was really good. Thank you very much, Neil. Are there questions from here? Yep.
Yeah. My question is, what's the mechanism of central X-ray emission?
Right. That's a good question, and it's not known. You mean in this instance, if there's late emission of X-rays, you're asking where would that emission come from? So, in a sense, at the moment, it's just a sort of an empirical observation that you seem to see this X-ray excess, and that if some of those X-rays are absorbed by the ejector material, then that could help explain the infrared brightening, because it could be re-emitted, the energy would be re-emitted in the infrared. The question is what might produce those X-rays, And the answers could be some kind of late accretion onto the remnant here. So there could be some accretion, so some of the ejecta may not be flung out, but may remain bound and be accreting slowly back onto the compact remnant. Could also be that you create not a black hole, but instead a very massive neutron star, highly magnetized, potentially highly magnetized neutron star, rapidly rotating, so a magnetar, and that itself could be spinning down and interacting with any material around it. That could produce spin down and drive energy into the material around it, and then that could potentially produce X-rays as well. So those are the sort of ideas, but it's still quite speculative.
I just can't understand why the emission is X-ray.
Well, why X-ray band rather than some other band? It obviously would depend on the temperature of the material doing the emitting, or the nature of the emission mechanism. So
More questions?
I suppose that's probably all there is to say. Yeah.
You made a mention this yesterday, but how small do you think the gravitational localization would need to be in order to make a confident association between a Killing array and gravitational?
Okay, let me think. I mean, if we imagine the scenario that a gravitational wave event has happened and it was thought to be a neutron star binary or a neutron star black hole binary, and we go off with VISTA and search this big error region and find an event which looks sort of plausible as being a kilonova and has kind of the right colors and the kind of right temporal behavior, and looks as if it probably exploded around about the same time, what can I say? I'm going to claim that that's a good candidate for being the counterpart. There's no doubt that those statistics obviously are difficult to do in a robust way. I mean, the problem is, I think there is a problem at the moment that we don't have a good idea of the infrared sky and the nature of all the unusual transients that might take place that would be unassociated with gravitational waves. So we have a good idea of the kind of more common ones, supernovae and maybe extinguished supernovae, but there are rare classes of supernovae and explosive transients, massive stars which are undergoing some kind of eruption, whose nature that we don't understand very well, and let's say they're behind some dust, and so that makes them look red. We see them in the near infrared. All of those things are potential imposters, and we know that there are not many of them, but to be honest, we don't have a very good census of them. And I guess this is where your question is going. Could you be fully confident? And I guess at the moment, I don't think you could be fully confident. I'm hoping that in the course of the next few years, by building up our understanding of the nature of those imposters and the number of them, that we will be able to say more confidently, okay, the chances of seeing an event like this when we did our follow-up program were, 1%, and there we saw one, and so, that gives us confidence. But I can't really put it down as, I don't think I could really pin down, what kind of error region would you need. What I can say is we don't see many, down to the depths we're looking in, we don't see many events in our VISTA data. There are not many supernova visible to these sort of depths in the infrared that we're picking up, certainly that are within galaxies which are within the sort of distance regime of interest, the 100 megaparsecs or so. So there are not a whole lot, but there could be some.
So with JWST coming up, is that going to be complementary in any way to finding kilonova? Or?
Yeah, I think very much so. So it should be much more capable than HST in many regards for following up the short duration GRBs in particular, assuming Swift is still flying, etc. The hope is JWST should possibly be a little more capable than HST is for TOO, target of opportunity observations, and clearly can go deeper. You could get much better spectral coverage of the light that you see. Now, the predictions for that are very sketchy at the moment, and so it's not necessarily the case that you'd be looking to exactly test the predictions so much as I think just explore the phenomenon and then use that as sort of input to the modelers so that they can then maybe try to understand the features that you see. So I think that's the way we'd be going with that.
Very small field, you need to find it first with a wide field survey from the ground. JWST is just too small to insert.
Right, so for the short bursts, assuming you've already got an afterglow, then of course you've got the localization. For a gravitational wave event, then you'd need to localize it some other way, as Stephen says.
Excuse me. In your plot, there's issue project. The last thing you will report the candidate of EM and gravitational wave correlation. Can you explain what is the candidate in your routine is and how to improve the confidence at each candidate? We will say, okay, this is probably the definite source. So how to define a candidate?
So I'm not quite sure I understand in the circumstance. So are you saying that in the future, if we find something right? Okay. Well, I think it sort of goes back to the answer I gave a moment ago that the sort of signatures we're looking for is we think we're looking for something which is infrared bright but faint in the optical. So we're looking for something we believe who's
Model dependent candidate.
well, that is model dependent. Exactly, that's right. But I think we can certainly say that you can use that to identify objects or to help identify the best candidates. And I think it really is a matter of putting all the information you have together, the distance you get if there's a host galaxy, the similarity or dissimilarity with other known populations of sources. So if something looks pretty much like it's more likely to be an unusual supernova, then that is probably something to ignore. But it's unfortunately we're not in a situation or at a stage in our understanding where you can give very firm criteria. So instead, I think it's a matter of bringing all the evidence you can and trying to weigh that up after the fact at some level.
Could you give me a rough feel for how much further how much deeper you can go if you were looking at just a square degree as opposed to 40 to 50 if you were tied in?
Yes, sure. Okay. Well, roughly you'd go, I suppose you'd go a magnitude or so deeper so it's with the Vista telescope. Of course, if you're looking at a small field of view, relatively small, then you could bring in other telescopes which would then become more feasible to use 8-meter telescopes and maybe use those instead, and potentially you could go deeper that way. But I think the problem is with those, they're really not set up to be trying to map very large areas.
Yes, okay, well, thank you all again there.
Thank you.